Welcome to the session on numerical methods, review exercises. The objectives for this session are to review previous topics through exercises, namely, understand what the domain and range of a function are and attempt related exercises, explore examples of differentiating functions with two or more terms, differentiate functions using the chain rule and product rule, and generate sequences from recurrence relations. We will now solve the review exercises shown on your screen. Pause the video and have a go. When you are ready to view the solutions, press play. Before solving the first exercise, we're going to take a look at some theory which will help us to solve it. A function is a mathematical relationship which maps every value of a set of inputs x to a single output f of x. The notation f of x is used to represent a function of x. The set of possible inputs for a function is called the domain, and the set of possible outputs for a function is called the range. Let's take a look at an example. The diagram will show how the function f of x equals x to the 4 maps values in its domain to values in its range. So suppose the domain consists of values 2, 4, minus 4, a third, and root 3. These all get mapped into the range. The 2 gets mapped to 16, that's 2 to the power 4. 4 gets mapped to 256, that's 4 to the power 4. Minus 4 gets mapped to 256, that's minus 4 to the power 4. A third gets mapped to 1 over 81, which is a third to the power 4. And finally root 3 gets mapped to 9, which is root 3 raised to the power 4. Now pause the video and have a go at this example. Press play when you're ready to view the solutions. So let's solve example 1a. So we have two functions f and g given by f of x equals 3x plus 5 and g of x equals x squared plus 3, where x is a member of the real numbers. We are required to find f of 3 and g of 8. We're going to look at f of x first and plug in x equals 3 into our function. So when x equals 3, we have f of 3 equals 3 times 3 plus 5. This is where x equals 3 comes from, and then plus 5, which is part of the equation, to give us 14. Now for g of 8. We're now going to look at the function g of x and plug in x equals 8. So we have g of 8 equals 8 squared plus 3, which gives us 67. And now for example 1b. We are looking at the same functions, but this time we're required to find the values of x for which f of x equals g of x. So if f of x equals g of x, then 3x plus 5 equals x squared plus 3. So now let's rearrange so that we have an expression which is equal to 0. We take all the values over to one side. X squared plus 3 is here, and we take minus 3x and minus 5 away from both sides to give us x squared plus 3 minus 3x minus 5 equals 0. We now tidy up. X squared stays as it is. Minus 3x stays as it is. And 3 minus 5 becomes minus 2. And of course all of this is equal to 0. We now solve by using the quadratic formula. Minus b is plugged in here. So minus b is of course minus minus 3, which is 3. b squared is minus 3 squared, which is 9. A is equal to 1. And c is equal to minus 2. And then we tidy up a little bit. And when we tidy up some more, we have x equals 3 plus root 17 all over 2, or x equals 3 minus root 17 all over 2. As shown. Recall that for all real values of n and for a constant a, if y equals ax to the power n, then dy dx equals an times x to the power n minus 1. A function with more than one term can be differentiated by differentiating terms one at a time. If y equals ax squared plus bx plus c, where a, b and c are real, then dy dx equals 2ax plus b. How do we differentiate multiple terms? If you can rearrange each term of a function so that it is expressed as ax to the power n, then you can differentiate the function one term at a time. In other words, if y equals f of x plus or minus g of x, then dy dx equals f dash of x plus or minus g dash of x, where f dash of x and g dash of x are the differentiated expressions of f of x and g of x respectively. So here's a summary of the key points. And here's exercise 2. We're going to take a look at part A first. If y equals x to the power 4 plus x cubed minus 2x to the power half, we have that dy dx equals this expression here. So for the term x to the power 4, we have that a equals 1 and n equals 4. And this gives us the resulting dy dx for this term. For the term x cubed, we have a equals 1 and n equals 3, and hence dy dx equals 3 times x to the 3 minus 1. And finally, for the term minus 2x to the power a half, a is equal to minus 2 and n is equal to a half. So we have this slightly complicated expression highlighted in red for dy dx for this term. We can therefore tidy up to obtain dy dx equals 4x cubed plus 3x squared minus x to the power minus a half. Let's now take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. In this example, we're required to find dy dx using the chain rule, given that y equals sin x plus cos x all cubed. So let's solve this. So here's y. We're going to let u equal cos x plus sin x, so the bit in brackets. U can be easily differentiated now. Cos x differentiates to minus sin x, and sin x differentiates to cos x, to give us this expression for du dx. We can also express y as y equals u cubed, and then differentiate to give dy du equals 3u squared. And now we can plug in these expressions into the formula for the chain rule to give dy dx equals 3u squared times cos x minus sin x. However, Notice that u was an expression which we introduced, so we must again replace this with cos x plus sin x as shown here, to give this expression for dy dx. The product rule allows us to differentiate the product of two functions, so if y equals u times v, then dy dx equals u times dv dx plus v times du dx, where u and v are functions of x. The product rule in function notation is as follows. If f of x equals g of x times h of x, then f dash of x equals g of x times h dash of x plus h of x times g dash of x. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to use the chain rule to differentiate y equals root 5x minus 1. So let's solve this. We're going to begin by letting u equal 5x minus 1, because this is the bit that makes it more tricky for us to differentiate y. We can now say that y equals root u, which equals u to the power a half. We therefore have that du dx equals 5 if we simply differentiate u with respect to x, and dy du equals a half u to the power minus a half. Now from the chain rule, we have that dy dx equals du dx times dy du. And so plugging in the different parts gives us that dy dx equals 5, which is the value of du dx, times a half u to the power minus a half, which is the expression for dy du. And since we introduced u, we need to plug in u equals 5x minus 1 as shown, to give us that dy dx equals 5 over 2 times 5x minus 1 to the power minus a half. Now let's take a look at part B. Given that y equals x cubed times root 5x minus 1, find dy dx. So let's solve this. We're going to begin by letting u equal x cubed and v equal root 5x minus 1. This will allow us to apply the product rule to y equals uv. Now differentiating u equals x cubed gives us du dx equals 3x squared. And from part A we have that the differential of root 5x minus 1 is 5 over 2 times 5x minus 1 raised to the power minus a half. And so we can apply the product rule. Dy dx equals u times dv dx plus v du dx, to give us that dy dx equals x cubed times 5 over 2 times 5x minus 1 to the power minus a half plus root 5x minus 1 times 3x squared. We can now tidy this up a little bit. Here's our fraction 5x cubed over 2 times root 5x minus 1. And for the second term, if we multiply the numerator and the denominator by 2 root 5x minus 1, we have this expression here. We can now tidy up the numerator to give us 35x cubed minus 6x squared, all over 2 times root 5x minus 1. And factorising this gives us this expression here. In a sequence, you can write a recurrence relation if you know the rule to get from one term to the next. The recurrence relation un plus 1 equals f of un expresses each term of a sequence as a function of the previous term. So, for example, the recurrence relation un plus 1 equals 4 times un minus 5 with the starting term u1 equal to 7 produces the sequence beginning 7, because of course we know that u1 equals 7, and then 23. We of course get 23 when we plug in u1 equals 7 in the equation u2 equals 4u1 minus 5. And then u3 equals 4u2 minus 5. And because we know that u2 equals 23, we plug that in to get 4 times 23 minus 5. And similarly for u4, which is equal to 4u3 minus 5, which is equal to 4 times 87, which is the value of u3, minus 5. The first term in the sequence must be known to generate a sequence from a recurrence relation. Now let's have a go at an example. Pause the video and have a go. Press play when you're ready to view the solutions. We're going to take a look at example A first. We are required to write down the first 4 terms of the following sequence. un plus 1 equals 5un minus 1 for u1 equal to 8. So let's solve this. We know of course that u1 is equal to 8. If we substitute u1 in the equation to find u2, we have u2 equal to 5u1 minus 1. Here, of course, we've put n equal to 1. And then plugging in the value of u1 into this equation gives us 5 times 8, which is the value of u1, minus 1, which is equal to 39. So we have that u2 equals 39. And now we substitute u2 in the equation to find u3. Here we've put n equal to 2 to give us the equation u3 equals 5u2 minus 1. We know that u2 equals 39, so plugging this in this equation gives us 5 times 39 minus 1, which is equal to 194. And similarly, plugging in n equals 3 in the recurrence relation gives us u4 equals 5u3 minus 1. And then plugging in the value of u3, which is 194, gives us that u4 equals 969. Now let's take a look at part B. We are required to write down the first 4 terms of the sequence un plus 1 equals 5un minus 1 with the starting term u1 equal to 11. Notice that the recurrence relation is exactly the same. However, U1 is different to part A. So let's solve this. We know, of course, that U1 is equal to 11. We can substitute U1 in the equation to find U2. So we have U2 equals 5U1 minus 1 to begin with. We've substituted n equal to 1 in the recurrence relation to obtain this equation for U2. Giving us 5 times 11 minus 1, which equals 54. And similarly for U2. We have this expression for U3 when we substitute n equal to 2 in the recurrence relation. And then plugging in U2 equal to 54 gives us 5 times 54 minus 1, which is equal to 269. And finally, to obtain U4, we plug in n equal to 3 in the recurrence relation to give us U4 equals 5U3 minus 1. And plugging in the value for U3, which is 269, gives us that U4 equals 1344. So here's a summary of our results. Notice that although the same recurrence formula is used for parts A and B, a different sequence is produced in both cases because U1 is different in each case. This brings us to the end of this session. If you have understood its contents, you should be able to understand what the domain and range for function are and attempt related exercises. Explore examples of differentiating functions with 2 or more terms. Differentiate functions using the chain rule and the product rule. And generate sequences from recurrence relations. Thank you very much for listening.